In Chapter 11, we're going to look at something called the chi-squared test. It's another test for inference. Alright, so a chi-squared test, and notice the symbol, it's a capital X squared. That's what we say, chi-squared. A chi-squared test for goodness of fit compares an observed distribution of categorical data to a hypothesized distribution. So, chi-squared test uses categorical data. Everything we've done up until now has been quantitative. But chi-squared is what we use when we have a set of categorical data. Now, goodness of fit is one type of chi-squared test. There's 3 of them, and we'll cover all 3 in this chapter. But the first one is just goodness of fit, and it's the simplest one. It's when you have one categorical variable that's measured from one sample or one population, and they usually give it to you in a table. So when you write the null and the alternative hypothesis, this is what it looks like. The null is that the stated hypothesis of distribution of the categorical variable, obviously in context, is true. The alternative is that whatever they claim is the distribution is not true or not correct, okay? So in theory, it's a two-sided test. It either is or isn't. That's like a two-sided test. It's not greater than or equal, greater than or less than. It's a not equals to. So, and you want to always, like always, in your null and alternative, you always want to state it in terms of the population, not the sample. Okay, so how do you calculate the expected counts for a chi-squared goodness of fit test? And should you round these to the nearest integer? So, expected counts are basically like, what would we expect to be true in our sample if what they claim is true? So, it's a real simple calculation. You're going to take your sample size and multiply it by the proportion that they tell you it should be. So if 80% of the population in this area is brunette, I take my sample size and multiply it by 0.80 to find out how many would I expect to be brunette. So things to remember, don't round these to a whole number. It's very common you're going to get a decimal, but that's okay. Don't round it to a whole number. It represents an average number expected in repeated samples. It's not an integer, it's an average. So don't resist the temptation to round. Now, what is the chi-squared test statistic? Here's what it looks like. This is the formula for it. Notice it's a sum. So we take the observed number, we subtract the expected number, square it, divide it by the expected number. That's for one category. All right? Then if there's multiple categories, we do the same thing for each category and then add them up. And that will give us a chi-squared value. Now, again, it uses the actual counts from a table, not proportions. So don't make them proportions, use the actual counts. And I'll model all of this for you in a little bit. And then what does this actually measure? It measures how different the observed distribution is from the hypothesized distribution. That's the goal of chi-squared. All right, in a goodness of fit test, when does the chi-squared statistic follow a chi-squared distribution? And then how do you calculate degrees of freedom for this goodness of fit test? Well, the chi-squared distribution is actually a right-skewed distribution, and I'll show you a picture of it on the next slide. But in order to follow that distribution, it has to have expected counts greater than or equal to 5. All right, so that's one of the conditions we'll look at. That you have to check all the expected counts and it has to be greater than or equal to 5. And then to find degrees of freedom, it's not very difficult. It's just the number of categories minus 1. Okay, notice that it does not depend on sample size. Traditionally with T-scores or T-stats, we would need a sample size, but with chi-squared, we don't. So then describe the shape, the center, and the spread of a chi-squared, and how are these based on degrees of freedom? Well, the shape, chi-squared is only positive. So if you think about a graph, it's only in quadrant 1. If chi-squared is 0, then that means that there's no difference between the null hypothesis and reality. Okay? If it's really significant, if it's big, that means there's a big difference and the sample values are not likely to occur by chance alone. All right, so as far as center, the mean is the degrees of freedom. And the peak, or the mode, would be degrees of freedom minus 2. Spread is this. Now, These values right here, you're rarely going to ever see. They're not on the formula chart. They're not something you have to remember. But you just got to know that the shape is going to be right skewed, meaning that when you calculate a chi-squared value, it's always going to be a positive value. All right, so how do you calculate a p-value using a chi-squared? So here's the picture I promised you. Notice that these are right skewed distributions, and the degrees of freedom does affect the shape a little bit. Okay, the degrees of freedom equal to 5, look, it's got a very sharp peak and then a long tail. And then if degrees of freedom is 20, meaning there's a lot more categories, it flattens out a little bit. Okay, so degrees of freedom does affect the shape, but regardless, they're both right skewed. So when you're going to need to find a p-value, you're going to go to your distribution menu in your calculator, and you're looking at chi-squared CDF. It's going to work a lot like the norm CDF function we've used before. So when you click on it, it's going to say, okay, what's the lower boundary, what's the upper boundary, and what's your degrees of freedom? So when you're thinking about these prompts, you need to think of it like a right-tailed test, because the lower boundary is going to be whatever your chi-squared value is, and the upper boundary will be like 10,000 or 1,000 or whatever. And then degrees of freedom is categories minus 1. So let me walk you through one of these tests. Jenny made a 6-sided die in her ceramics class and rolled it 60 times to see if each side was equally likely to show up on top. So, A, state the hypothesis Jenny is interested in testing. Well, she wants to know if her die is a fair die, right? So we're going to use an alpha of 0.05. Since it's not stated, that's our default. So my null hypothesis would say each outcome of a 6-sided die is equally likely to occur. That's the definition of a fair die, right? That's what we're testing to see. So the alternative then is that each outcome of the 6-sided die is not equally likely to occur. All right, assuming that her die is fair, let's calculate the expected counts for each possible outcome, all right? So if there's 60 times she rolled it, let's think about this. For a fair die, each number has a 1 out of 6 probability, right? So the expected count for each number will be 60 times 1 out of 6. Doesn't matter if it's a 1, 2, or 3, the probability is the same, right? So for each outcome, the expected count is 10. All right, so part C, it says, here's the results of the 60 rolls that she made. Calculate the chi-squared statistic. So these are the outcomes of the die, and then how many times did that come up in her 60 rolls? So notice, it's not perfectly 10 every time, right? Our expected counts were 10, but these are the observed counts. So we use our formula. We plug in the observed count minus the expected squared divided by the expected. And then I do the next observation, or the next outcome. 11 minus 10 squared over 10. Now, the 10s, in this case, they're all 10 expected counts, right? They're not always going to be exactly the same, and you'll see that as we go through the chapter. But as far as the formula, I don't have to show all 6 outcomes. I just show the first couple, and then you're going to use your calculator. So I'm going to show you how to do that. So here in your calculator, what you're going to do is go to your list, and you're going to input your observed counts in list 1, and then the expected counts in list 2. And that's what I've done here. Then I'm going to go to my test menu. I could use chi-squared CDF, but I think it's easier to use the test. So you go to stat test, and it's test D, so you have to scroll down on your screen to chi-squared GOF, that's goodness of fit test. When I do that, this is what comes up. Where's the observed, where's the expected, and how many degrees of freedom? Well, I had 6 outcomes, so I have 5 degrees of freedom, and they're in the right places. So then I just hit calculate, and this is what it'll tell me. So there's my chi-squared. It's 3.4, and there's my p-value, and there's my degrees of freedom. So I need to make sure to write down chi-squared, degrees of freedom, and then p-value to get full credit for this, all right? Okay, so part E says to make the appropriate conclusion. So I take my outcomes on my calculator, and I realize the p-value that they gave me is 0.639. All right, so then I'm going to draw my conclusion like I always would, connecting p-value to alpha. So I say because the p-value is 0.639, and that's greater than 0.05, we fail to reject the null hypothesis. There is not convincing evidence that the die is unfair. Remember, that's what the alternative said, is that they're not equally likely, which would mean unfair. So we don't have convincing evidence that it's unfair. That's how you work a goodness of fit test.